Welcome to Minerva Tutors TV and the GCSE/IGCSE Chemistry series. Today we're going to be looking at atomic structure, which is one of the more important topics on the exam because one, it always comes up, and two, every other topic in chemistry links back to this and requires a good knowledge of this topic here. So we'll start off with atoms. Atoms are the smallest part of an element that can exist. Every single element is made up from a different type of atom, and as we can see from this diagram here, they're made up of two key parts: the nucleus in the center and the shells that orbit around it. The nucleus is made up of two things. It's made up of protons and neutrons. These shells contain electrons. And if we look at two different elements, so in this case hydrogen and oxygen, we can see that they have different amounts of protons, neutrons and electrons. So the hydrogen atom is much smaller than the oxygen atom, simply because it only contains one proton, one electron and 0 neutrons. The oxygen atom contains 8 protons, 8 electrons and 8 neutrons. This gives it different properties. It means it behaves slightly differently to hydrogen and also slightly differently to every other element in the periodic table. Now, if we combine two elements together in a chemical reaction, we form what we call compounds. So again, compounds are formed by combining two different atoms or more in a chemical reaction, and they're chemically joined together or chemically bonded together. So this example over here, we've got water. Water comes from hydrogen and oxygen chemically reacting together, forming a chemical bond, which is represented by these lines here, to form the compound water. Another example of a compound, carbon dioxide. Carbon dioxide is when carbon and oxygen chemically react together, again, to form bonds, creating the compound of carbon dioxide. Now, we can normally tell when a chemical reaction is happening because it will either give off some sort of physical indicator, like a change of colour, fizzing, maybe some heat loss or heat gain, and that will be a good indication that a compound has been formed from elements reacting together. Now, we can still mix elements together and not form a compound. There cannot be a chemical reaction taking place. That'd be a mixture. So here I've got an example of a mixture that's quite common, and it comes up in exams quite a lot, where we've got a compound of water, H2O, being mixed in with another compound, which is salt. Salt is sodium chloride. Sodium atoms and chlorine atoms chemically bonded together to form the compound of sodium chloride or salt. But when we mix these two compounds together, they don't react. They don't chemically react. They just mix in with each other. You can see there's no bonds between the water and the salt there. They're just mixed together. They're forming a mixture in that case. So going back to an atom, like we say, an atom's made up of protons, neutrons and electrons, and there are a few key things we need to know about protons, neutrons and electrons, and I've put them in a table for you on this slide here. And this table is really important to remember because often they will simply give you a blank table like this and ask you to fill it in as the question. If they don't, they'll often ask you a question on the charges or the mass or the location of protons, neutrons and electrons, so they're easy marks to be able to remember. So starting off with protons, they're located in the nucleus of the atom, again the center. They have a mass of 1. Now that's a relative mass. It doesn't mean we've got 1 gram, 1 kilogram, 1 pound, 1 stone, nothing like that. It just means that compared to neutrons and electrons, they weigh 1. They've got a relative mass of 1. They've got a charge of +1. They're positive protons. Moving on to neutrons, they're again found in the nucleus and again have a relative mass of 1. They weigh about the same as what a proton weighs. Neutrons are neutral. Neutrons neutral. They've got no charge, like so. The last one, electrons, they're not found in the nucleus, they're found in the shells orbiting around the nucleus. They have a mass of about 0 or a negligible mass, meaning that their mass is so small compared to protons and neutrons, we can just say it is 0, very, very small. They've got a charge of -1. And the reason for that is they need to balance out the positive charge of the protons. So the atom overall, when it's in its element form in the periodic table, needs to be neutral overall. So we'll often find that we've got the same amount of protons as we do electrons to balance that charge out and create a stable atom. Now, we didn't always think that atoms look like this. We found out that they look like this with the shells and the nucleus in the center by this experiment, the alpha particle scattering experiment. Previously, we used what was called the plum pudding model to sort of indicate what an atom looks like. We said it was a big ball of positive charge with negatives dotted around it. And that would be next to another big ball of positive charge with negatives and another one, meaning that any element would be completely solid, atom to atom to atom to atom. Now, if it was completely solid, what we would have expected when we fired alpha particles at it is for those alpha particles to be deflected straight back, kind of like hit a tennis ball being thrown against a wall. It comes straight back at you. But what actually happened was some of them were deflected to the sides, so sort of down this way and that way, but a lot of them ended up going straight through the gold foil. Now, what this indicates is there's a lot of empty space for these alpha particles to pass through in this gold foil. And that's how we came up with today's atom, which again looks something like this here with the electrons in these shells, but there is a lot of empty space in the shells where the electrons aren't present. So that's where the alpha particles will be able to pass through in that experiment. Now, the periodic table gives us every single type of atom that has ever been discovered, and as far as we know, that can be discovered at this point. It also tells us two numbers, or gives us two numbers. It gives us a smaller one, which if I use copper as an example up here, we've got a smaller number. This is the atomic number, sometimes also called the proton number. On the bottom, we've got a larger number. This is the mass number of copper. And if I zoom in on a few of those elements, like here, I've chosen hydrogen, nitrogen, and gold. The atomic number for nitrogen is 7. This tells us the amount of protons. Like I said before, it's sometimes called the proton number, and it helps us out a bit when they do call it the proton number, because it reminds us that it is simply the amount of protons. So a nitrogen atom will have 7 protons. Now, because, like we said earlier, in the elements on the periodic table, the amount of protons is the same as the amount of electrons, nitrogen will also have 7 electrons. The bottom number, or the larger number in this case, is 14 for nitrogen. This is the mass number. The mass number represents the amount of protons plus the amount of neutrons. Again, because protons and neutrons weigh 1, electrons, we say they've got a negligible weight. They don't really weigh anything, so we don't count that in the mass number. So this mass number of 14 tells us that together, if we were to add up the amount of protons and neutrons in nitrogen, we'd get 14. So we can easily calculate the amount of neutrons in nitrogen by doing 14, take away the 7 protons, meaning there must also be 7 neutrons in this one here. If we look at gold as another example, you can see the proton number, or the atomic number at the top, is 79, so it must have 79 protons. We can see the mass number is 197 here. If we were to take them away from each other, we would know that we've got 118 neutrons in gold, like this, and of course 79 electrons, because that's the same as the amount of protons. Like so, what we can then do with this information from the periodic table is we can then go on to draw what the atom or the atomic structure will actually look like, and what the electron shells will actually look like. So another example I've chosen is sodium. Sodium has a proton number, or an atomic number, of 11, meaning it's got 11 protons, but of course it means it's got 11 electrons as well. So we can draw in these electrons, and we draw them in the following way. We draw them in, the first shell contains 2 electrons, a maximum of 2. The next one, and the one after that, and the one after that going on, can take a maximum of 8 electrons. So with sodium, we've got 2 in the first shell, 8 in the next one, and then 1 in the outer shell to make up our 11. 2 plus 8 plus 1, giving us our 11 electrons. Then we can do this for any atom in the periodic table, although they actually only ask you to do the first 3 rows. They won't make you go much larger than that because it just takes up too much room and takes up too much time in an exam. So the final thing we're going to be looking at in this section is how we calculate the relative atomic mass from things that we call isotopes. So an isotope, or an isotope of an element, is 2 elements or two samples of an element that have the same amount of protons but different amount of neutrons. So for example, in this question here, we've got carbon-14 as one of the isotopes and carbon-12 as another isotope. They've both got different mass numbers. That's what the 14 and the 12 stands for. One's got a mass number of 14, one's got a mass number of 12. Now they'll have the same amount of protons. They both got 6 protons, meaning that the carbon-14 in this case has 2 extra neutrons compared to the carbon-12. And that's fine. I mean, it still behaves like carbon. It still looks exactly the same. You wouldn't be able to tell the difference by eye unless you were to look at the amount of neutrons each atom has. But it's just the different ways that these elements can exist. The abundance is the other thing mentioned in this question. And the abundance simply means how much in percentage do we have of each of these isotopes. So the question here is saying that we've got 2 isotopes, one carbon-14, and we've got 20% of this carbon-14 in our sample. We've got the other isotope, carbon-12, that's 80% abundant. We've got 80% of it being this carbon-12. It now asks us to calculate the relative atomic mass. Now to do this, we use this very, very straightforward formula that looks something like this, where we're taking the mass of isotope 1 and timesing it by the abundance of isotope 1. So in this case, the mass is going to be the 14 and the abundance is going to be the 20 here. We're then putting that in a bracket and we're adding that to the mass of isotope 2 times by the abundance for isotope 2, like so. And then we're putting it all over 100. And that 100 has come from adding together our abundances, 80 and 20%. It will normally be add up to 100, but it's always good to check just in case with that one. So this is our first step here. We can see we've got the 14 times the 20 plus the 12 times by the 80 all over 100. If we go through and put that into our calculator through the next stages, we can see that the 14 times by the 20 gives us 280. The 12 times by the 80 gives us 960. We add those two together to get 1,240 over 100. And finally, if we throw that into a calculator, we get a relative atomic mass for carbon of 12.4, like that. So very, very straightforward steps. I'll give you one to have a go at. So if you want to give one a go, I will pause the video now and you can give this one a go and then we'll talk through the answer afterwards. So hopefully you all had a go at that one. As you can see, we've got a relative atomic mass for iron of 55.914 here. What we've done to get that is we've paired up the mass numbers with the percentage abundances. So we've got iron 54 being the first one here. It's the abundance was 5.8%, so we paired those two together, times them, put them in the bracket and added it to the 56 times by the 91.8 and the 57 times by the 2.1 and the 59 times by the 0.3. We put that all over 100 because our percentages added up to 100, and then we threw that into a calculator and it's given us once again the 55.914 relative atomic mass for iron there. Great, so that's the end of this topic. We've looked at the structure of an atom, we've looked at the difference between elements, mixtures and compounds, and we've also looked at how we can find the relative atomic mass given the abundances and mass numbers of isotopes. Don't forget you can carry on with this series and look at the next video in the series, which is looking a bit deeper into the periodic table, the groups in the periodic table and why it is structured as it is.